Hi, this is a short explanation about friction. Now if you imagine that we have a box on a level surface, then this box will not move by itself. You will actually have to apply some force, let's call it F, to move the box. And because you have to apply some force to actually make this box move, there must be some reaction force. And this reaction force is called friction. So in this case, the reaction force goes into the opposite direction. Let's call it FR for force of friction. So now that we have established that we have to have some reaction force, let's actually draw in the other forces into this box as well. So this box has some weight, mg, and there will be some reaction force on the y-axis as well. Otherwise, this box would just fall through the ground. Let's call this one Fn, n as in normal. Remember, normal is anything that's perpendicular. Now you can imagine that in order for this box to not move, or in other words, for this box to be in equilibrium, that the friction force and our force that we're pushing it with, F, must be equal. So, in other words, we can say that F equals Fr. So, the force that we apply equals our friction force. But we also can express this friction force by our normal force and some coefficient. So, some coefficient called S for static, and our normal force will be the same as our friction force. And this here tells us that friction is only dependent on the weight. It is not important how big the contact surface area is. It's only important what the weight, so in this case our reaction force 2mg, which is in this case Fn is, and what the friction coefficient mu s is, which always depends on the materials that we use. Okay, so this here is valid for the static case. This is why we're using the mu static. But what happens, or what do we need to do if we actually want to move the box? In that case, the force that we apply, our F, actually has to be larger than Fr. Otherwise, the box would still be stationary. And once the box is actually moving, we can say that Fr, and once the box is actually moving, we can say that our reaction force is equal to a different coefficient, in this case mu kinetic times our normal force. Mu kinetic is usually 3/4 of our mu static, which means we need less energy to keep the box moving than we needed to start it moving. This can also be expressed in a nice graph. So if we imagine a box that's sitting on an incline with some mass m, and it's on Earth, so we have some gravitational acceleration, then this of course is some downward force, and this box will have some kind of normal force that's going into the opposite direction, or at least in the y part of this box. So we have some normal force, and then the x part is taken care of by our friction force, so our Fr. So now to get back to the point that I was talking about earlier, that our mu static is bigger than our mu kinetic, can be seen in this graph of this box over time. So if we on one axis plot the FFR and on the other our time, then we can see that the reaction force of the friction becomes larger and larger, larger and larger with time, until the maximum friction force is reached and it cannot get any bigger, and our mg takes over. Then we actually have a sudden drop in friction force, which then is linear. So at this point right here, our box starts to move. And here it's actually moving all the time, and here it's stationary. So this is stationary, and this is kinetic coefficient. And you can see that the stationary coefficient is bigger than our kinetic coefficient in this case, because both of these are always multiplied by our normal force. Okay, I hope this could help you.